Hello guys, today we're going to be doing the physics region from June of 2025. Alright, part 1 as per usual is going to be multiple choice questions. How you start off with most of these type of questions is I identify the quantities that is given to me, and then I try to find like an equation that relates to those quantities. It might be in some cases where I will have to solve for another quantity before I can move on. So yeah, okay. Alright, base your answers to questions 1 and 2 on the information below and your knowledge of physics. A car initially moving at 20 meters per second travels 200 meters while accelerating uniformly to a speed of 30 meters per second. So we have the initial speed, that's going to be 20 meters per second. That's going to be my initial speed, and it travels 200 meters, that's my distance. And then top speed, so that's going to be my final velocity. And the equation that relates those three, actually, wait, let me read the question. The magnitude of the acceleration is, so the acceleration, that's what I'm being asked for here. So, the equation that relates these kind of like four quantities together is Vf squared. So, final velocity squared is equal to initial velocity squared plus 2AD. All right, what's the magnitude of the acceleration? So I'm going to solve for A. So Vf squared minus Vi squared all over 2D is equal to A. And now just plug it in. So Vf is 30 squared minus 20 squared over 2 times 200. And I get 5/4, which is 1.25, and it's answer choice 2. Okay, the time required for the car to travel the 200 meters is, so now that we have a new quantity, which is acceleration, I'm going to focus on initial velocity, final velocity, and the acceleration. It is an easier equation that relates those two. It's pretty easy. The most basic equation is final velocity is equal to initial velocity plus A times time. So to solve for time, I'm going to do Vf minus Vi all over A is equal to T. So Vf is, my final velocity is 30 minus 20 over 1.25. That gives me a time of 8 seconds. So the answer is 2. A car traveling at 12 meters per second north accelerates in a straight line at 3 meters per second square north for 4 seconds. How far north does the car travel during the 4-second accelerate? So I'm first given the initial velocity, and I'm given that it's accelerating. So the initial velocity was north, and then the acceleration is also north, so it's in the same direction. So A is going to be positive. And for 4 seconds, that's going to be my time. How far north does the car travel? So we're looking for the distance here. So which quantity relates those? We have D equals to VIT plus 1/2 AT squared. And I'm just going to solve. Well, I'm just going to plug in. So VI is 12. T is 4. And then plus 1/2 A, which is acceleration, so it's 3, T squared, which is 4 squared, and I get 72. So the answer for number 3 is 4. Okay, a block weighing 4 newtons rests on an component shown in the diagram below. What's the magnitude of the component of the block weight perpendicular to plane? So 10 newtons, that represents the force downwards. If it's perpendicular to the plane, we're going to use cosine. And if it's parallel to the plane, so going down the plane, is going to be sine. So in this case, we're going to use cosine. And why this works, it's a little bit of trick. And I don't really want to go over that right now. So yeah, it's going to be 10 times cosine of the angle to the horizontal. So it would be 30 degrees. So 10 cosine 30 degrees. And as you're solving this, make sure your calculator is in degrees mode. And you should get 8.66, which is to like it's closest to 8.7. Okay, a sailor is near the top of a sailboat mast. The sailboat is traveling at a constant velocity of 5 meters per second west. The sailor drops a screwdriver that falls freely for 1 second before hitting the deck of the sailboat. And where does the screwdriver land? So is it going to be directly below the sailor? Is it going to be behind the sailor, in front of the sailor? So let's just figure that out first. So when you drop it, right, when you're on a sailboat, so let's say you're on a boat. If the whole entire boat is traveling at a constant like velocity, right, everything on the boat is going to have that velocity. So if you're standing on the boat, you're also going to have that velocity. So the sailor is going to have that constant velocity, and so is the screwdriver. When you drop it, the screwdriver is still going to have that horizontal velocity. So since we're neglecting air friction here, the kind of like the horizontal distance that it travel, it should be the same for the sailboat, for the sailor, and the screwdriver. So in this case, it would be directly below the sailor, because with respect to each other, there shouldn't be any like change in the horizontal distance travel. And one thing to know is that for when we're dealing with like projectile motion, kind of like doing stuff off like a cliff, just remember the x and the y components are independent of each other. So that's also something to know for this. Okay, a marble is projected horizontally from a fixed height above a level floor. If the marble is projected horizontally again from the same fixed height but twice the initial speed, its time of flight will be. So we kind of have this over here, and the marble is being thrown off the cliff like this. But then remember what I just said, the x and the y components are independent. How long it stays in the air for depends solely on if there were any initial velocity in the y direction, so any vertical initial velocity, and there's no change in that, so therefore there would be no change in the flight time. All right, there will be a change in the trajectory with how far it travels. There will be a change in the range. In this case, it would be an increase because the initial speed was increased. All right, which animal has the greatest inertia? So when it's asking about the inertia, mass is basically like inertia. So the higher the mass, the higher the inertia. So in this case, greatest inertia, we're going to look for the animal with the greatest mass. It doesn't matter how far they travel, how fast they travel, if they're stationary or not, but the answer is choice 4 because it has the greatest mass. Okay, a car is rolling in a straight line on an inclined ramp. The car is in equilibrium when it's rolling up or down the ramp with. So when something's in equilibrium, that means net force is equal to 0. That means the acceleration is on the object is going to equal to 0. So acceleration means that there's a change in the speed. So is it increasing speed, decreasing speed? Neither of them, because if there's a change in the speed, then my acceleration is going to be non-zero, whether it's constant acceleration or constant speed. The answer is constant speed. Constant speed means that the speed is not changing, so therefore no acceleration. If there's a constant acceleration, then it could be like 1 meters per second squared, 2 meters per second squared, etc. So that doesn't really make sense. The answer is 4. A 3-kilogram bowling ball and a 7-kilogram bowling ball are in free fall near the surface of Earth. Compared to the magnitude of the acceleration of the 3.5-kilogram ball, the magnitude of the acceleration of the 7-kilogram ball is. So the magnitude of the acceleration, for these type of question, we're neglecting air friction and stuff like that. So the acceleration is going to be the same. It's going to be negative g, where it's going to be like g pointed downwards, and that's going to be 9.81 meters per second squared pointed downwards. And that's going to be the same for all objects, regardless of their mass. The mass is independent. Okay. All right, the diagram below represents a 600 Newton student standing in an elevator. The elevator floor exerts an upward force of 400 newtons on the student. The student has a weight of 600 newtons. So 600 is going to point it down. And the elevator exerts an upward force of 400 newtons. So upwards is going to be 400 newtons. If we do the net force is going to be 200 newtons down. And the net force is going to be 200 newtons downwards, because upwards you have 400, downwards you have 600. The more is going to take the direction, and 600 minus 400 is equal to 200. So if net force is pointed downwards, then that means there's acceleration pointed downwards. So the answer is choice 3. Okay, on one end of a spring is held stationary, and a 40 newton force is applied to the free end of the spring. So we have a force here. Elongates the spring 0.2 meters from its unstretched length. So we have a distance here. What is the magnitude of the total force required to stretch the spring? So we have another distance here, 0.8 meters from its unstretched length if the spring's elastic limit has not been exceeded. So let's look at the first part. One of the spring is held stationary, and a 40 newton force is applied to the free end, and it's elongated by 0.2 meters. So we can use Hooke's law, and we can kind of like give like a little bit of like the spring constant. So we know that Fs is equal to Kx, and I'm going to solve for the spring constant using kind of like what is like a situation that does work. So K is going to be X over Fx. So this should be Fs. So X is equal to, so X is 0.2 and then divided by 40. And that's equal to 0.05. And we don't want to exceed the spring constant, because if it's higher, then it's like, you're gonna risk like going over that constant, and it's not gonna work. So we want to stretch it 0.8 meters. So now we just gotta use the same equation, Hooke's law again, and then I'm gonna plug in 0.05 for K, and then for X, I'm gonna put the new distance, which is equal to 0.8. So that is gonna be wait, hold up, I made a mistake somewhere. Hold up, I made a mistake in the beginning. I'm so sorry, guys. Let me scratch this. Okay, I solved for K incorrectly. So K is actually Fs over X. So K is going to be 40 divided by X, which is how far is stretched by. Actually, I'm going to change this to X to be consistent. So then it's going to be 0.2. So the spring constant is going to be 200. I'm going to use Hooke's law again. It's going to be 200 times the new stretch length, which is 0.8. So the maximum, the total force, it would be 160. The answer is choice 4. Okay, the engine of a toy train is traveling at a constant speed or on a horizontal circular track. So we know we have constant speed and we have a horizontal circular track. If the speed of the engine is double the magnitude of the centripetal acceleration of the engine is. So let's look at the equation for the centripetal acceleration. AC is equal to V squared over R. So if the speed is doubled, then I have 2V. So V becomes 2V. So then I have AC is equal to 2V squared over R, which is equal to 4V squared over R. And you'll see that this is 4 times. So it would have been quadrupled. The answer is 4. The length of an electric field has a magnitude of 3.5 times 10 to the power of 5 newtons per coulomb. So that is the electric field strength. Let me just double check what the variable is. So this is E. So this would be my E. And then what is the magnitude of the electrostatic force? So this is what I'm being asked for, Fe, on a 5.3 times 10 to the negative 6 coulomb charge in this field. So this would be my charge, which is Q. And we can kind of see which equation relates those two. Which equation relates those 3 quantities. E is equal to Fe over Q. And I'm solving for Fe here. So Fe is equal to E times Q. And for these, I would like to use something called the double E notation on your calculator. It makes typing things a little bit easier. So E is going to be 3.5. And I'm going to use the double E function on the calculator. This here is 3.5 times 10 to the 5th power. That's just in scientific notation. Makes it a little bit easier to type in on the calculator. And then you just type that in. E5. And if you don't know where the E is, the double E is going to be, you press second. Well, this is on the TI 84. Is you're going to press second and you're going to press the comma. And you see the double E in blue. That gives you 1 E when you type it in. I'm not sure why they have that, like as in like E on the button, but then on the screen is singular E. But yeah, anyways, this rounds up to 1.9 newtons. So yeah. Okay, a car is traveling on a level highway at a speed of 15 meters per second. So we have a velocity here, a braking force. Okay, it sounds like this is the initial velocity because we're braking, so the speed is going to decrease. Braking force magnitude of 3 times 10 to the 3 newtons. So this is the force. Brings the car to a stop in 10 seconds. So this is going to be my time. The mass of the car is... Okay, so we're solving for the mass here. And this is going to require us to solve for something beforehand. We're going to have to solve for the acceleration. So acceleration, again, we have... So another force that's kind of like hidden is the final velocity. It comes to a stop. So it says that, we're modeling it so that it comes to a stop. So we know that this is equal to 0. So then we have F is equal to VI plus AT. And I'm solving for A, so VF minus VI over T is equal to A. So my final velocity is 0 minus I, which is 15, divided by time, which is 10. So my acceleration would be negative 1.5. So now let's find the magnitude of the force that acts on it. So we have F is equal to ma. We do have one of Newton's laws. I'm going to take the magnitude of it. So, because this is more supposed to be like the magnitude. But yeah. It's going to be, I'm going to solve for mass. It's going to be F over A. So M is going to be, so the force, which is, the force is 3E3, and then divided by the acceleration, which is 1.5. So the force is going to be 2,000, and it would be 2 times 10 to the power of 3. So the answer for number 14 is 2. Okay, a 5 kilogram traveling, so a 5 kilogram car, so we do have mass traveling east at a speed of 15 meters per second, so that's the velocity, collides with the 10 kilometer car. Okay, so I'm going to do M1, V1 with the 10 kilogram car, so that's M2, traveling west at a speed of 15 meters per second, so that would be my V2. The total momentum of the two-car system after the collision is, so here we have a conservation of momentum. P before is going to equal to P after. So now, basically, we just got to find the momentum before. So the momentum is going to be M1, V1, so the momentum of the first car plus the momentum of the second car, M2, V2. So momentum, the total like momentum in the system, you just got to add it up. Okay, we got to be a little bit careful here, because then one is traveling east and one's traveling west. So let's make east positive and west negative. So I'm going to do 5 times negative, I'm going to do 5 times actually positive 15 plus 10 times negative 15. And notice how I made the west negative, because that's what I set it as, and gotta be consistent now. So this would be negative 75, and we set negative to be west, so the answer is choice 1. 75 kilograms times meters per second west. Okay, in the diagram below, a force acts right on proton P in an electric field. To produce this force, the direction of the electric field at the position of the protons pointed towards, it would be pointed in the same direction as the force, so the answer would be the direction of the electric field would be in the same direction, so it would be choice 3. Okay, while investigating static electricity, a student noticed a negatively charged plastic rod tracks a small piece of paper. The student correctly concludes that the charge of the paper is, so the paper, so we know for sure it's going to be positive because opposite charges attract, but I have to know that it might be positive or neutral. So the answer to number 17 is 4. And you kind of think of this as like with like water, because if you rub a pipe and you put it near water, you can kind of see some attraction there. But water, it's not necessarily positive, it's more neutral, so it could be neutral or positive. Okay. The diagram below shows a 1 kilogram cart moving to the right at 1 meters per second and is about to collide head-on with a 2 kilometer cart moving left at 2 meters per second. During the collision, the magnitude of the force exerted on the 1 kilogram cart by the 2 kilogram cart is F. What is the magnitude of the force exerted on the 2 kilogram cart by the 1 kilogram cart during the collision? This one is going to be the same, because when you have two forces act on each other, when you have like a collision, right, whatever the magnitude of the forces that happen to like each of them is going to be the same. All right. Sunlight shines on solar panels on the roof of a house. The panels are hooked up to the house's electrical system, which is used to operate a microwave oven that heats up a cup of coffee. What energy conversions are taking place in this process? So we first have sunlight, which is an electromagnetic light. Is electromagnetic energy. So if we look over here, we have the electromagnetic spectrum. Sunlight will have like kind of like a lot of these. So we will start off with electromagnetic, so we can eliminate 2 and 3. And then now it's onto solar panels. And then what happens in solar panels is that light energy is being converted into electrical energy. So we can kind of eliminate 4, which is left with 1. The answer to 19 is 1. And then when we have electricity, it's gonna convert. So in the oven, not in the oven, in the microwave, it's gonna convert into microwaves. and then the microwave heats up the food, so that's thermal energy. So for number 19, the answer is 1. Okay, which graph best represents the relationship between the potential difference across a resistor and the resulting current through the resistors for a resistor that obeys Ohm's law? So if you're here, the two type of relationships that we have to know is direct, where we have y is equal to kx, or inverse, which is y is equal to k over x. So let's look at Ohm's law. And if you remember, Ohm's law is R is equal to V over I. And this one we're looking at potential difference, which is my V, and my current, which is my I. So you know what I'm going to do? I'm going to make it so that it looks like one of these. So I'm going to do R over, I'm going to do V is equal to R times I. All right. And here, this looks like a direct relationship. So the answer would be choice 1. So this is a direct relationship. And this one would be this would be a positive direct relationship. This would be a negative direct relationship. And 3 would be an inverse. And then 4, no matter how we change the current, the potential difference stays the same. So there's no relationship between the two. All right. As shown in the diagram of the pendulum below, mass m is released from rest at point A and allowed to swing through a point B to point C. Okay, compared to the kinetic energy of mass m at point B, the kinetic energy of mass m at point C is. So, when it's at the highest, we're going to have all potential energy. And then when it's at the lowest, we're going to have all kinetic energy. And then you kind of see how, like, since we have a conservation of energy here, it's going to fluctuate from having potential energy. It's going to have a combination of potential energy and kinetic energy in any point in between. So at point B, then C. So C is going to have all KE. So this is going to have all KE and 0 PE, 0 potential energy. So B is going to have more potential energy but less kinetic energy. So this is going to be height, and we have a conservation here. So all of the is going to be half as great. So we're going to eliminate twice. We're going to eliminate the same. We're going to have greater. And because for potential energy, we just have mg change in height, or mg times the height. And you can see how the potential energy, like, it just halves. So all that potential energy becomes kinetic energy, since we're neglecting friction here. All right. A student running at 6 meters per second slides to rest on a horizontal floor. As the student slides, the internal energy of the student floor system. So when the student is sliding here, why is it sliding? Why is it slowing down? It's because of friction. And, when the student is moving, it's going to have some kinetic energy. And friction is going to, decrease that kinetic energy so that the student doesn't have any kinetic energy and comes to a stop. Where does the energy go? Energy, it dissipates. And this is what we call internal energy. So the internal energy would increase, so that could be like sound, that could be like heat and stuff, and then the kinetic energy would decrease so that it becomes 0, so that the student would slow down or eventually come to a stop. So the answer is choice 2. Okay, which object will most likely produce a magnetic field? So if we have a magnetic field, we need moving charges. So here the answer would be choice 4, a moving charged object. All right, to reduce electrical resistance of a copper wire, increase the wires. So let's look at the equation. What I like to do is look at resistance is equal to rho, which is a constant. Rho is the resistivity. So we have a constant. It's going to be different for each material times the length over A. So if I want to reduce the electrical resistance, I would have to increase the diameter, and the diameter would change up the area. So 24, the answer is 3. If we increase the length, it's going to be more resistant. And then the temperature, higher temperature is more resistant. And the resistivity, if we increase the resistivity, then of course the resistance would increase, given that everything else stays the same. Okay, the potential difference of 12 volts, so this is the V, is applied across a resistor. So we're going to have some resistor for 60 seconds. That's going to be out of time. A constant current of 0.1 ampere, so this is going to be my I, travels through the resistor during this time. What is the power of the resistor? All right, so okay, power is equal to V times I. So this is going to be 12 times 0.1, and it would be 1.2. 25 is 1. So we look at this equation over here. Okay, what type of waves are sound waves? So you kind of have to remember sound waves are not electromagnetic waves. So if they're not electromagnetic waves, it can be an ultraviolet waves, because UV rays, they are part of the electromagnetic spectrum. So is it longitudinal or is it transverse? So longitudinal versus transverse is how they kind of like how the particles move. So if this is the direction of motion, transverse waves will move up and down. If it's longitudinal, it will move side to side. So in this case, sound waves are actually longitudinal. They move side to side. The answer is choice 1. Okay, as waves travel through space, they transfer. So this one is kind of like a memorization problem, and it's going to be energy. Because waves, we kind of think of them only having energy and no mass, so only energy is transferred. Okay, the frequency of an orange wavelight is, so we have the frequency, that's going to be F. The wavelength in a vacuum, so we're looking for the wavelength here. So let's look at the waves. The wavelength is going to be lambda. So we have V is equal to frequency times lambda, and V is going to be the speed of light in a vacuum. So we're solving for wavelength. So V over F is equal to the wavelength, and we look at the constant of speed of light in a vacuum. That's going to be C. That's going to be 3E8. So it's going to be 3E8 divided by the frequency, which is 4.85 E14. So it will be 6.1855 E negative 7. So the answer is choice 4. Okay, which statement describes mechanical and electromagnetic waves? So mechanical waves, they require a medium to travel through, and electromagnetic waves do not. So electromagnetic waves can travel through space, which is a vacuum. It does not have any doesn't have any matter, so it can't really like travel through. So mechanical waves can't really travel through space. So mechanical waves all travel at the same speed in a vacuum, whereas the speed of electromagnetic waves vary in a vacuum. So electromagnetic waves, they all travel at the same speed in a vacuum, like in space. Electromagnetic waves have the same frequency, whereas electromagnetic waves all have the same period. So that's not going to be true. They have different frequency and different periods. Mechanical waves require material medium through which to travel through, so that's correct. Whereas electromagnetic waves can travel through a vacuum. So I kind of gave that definition in the beginning. I didn't redo the answer choices. I kind of gave that out, and that's something that you should think about when they ask you this type of question. Mechanical waves are transverse waves, whereas electromagnetic waves are longitudinal waves. So that's incorrect. Electromagnetic waves are transverse waves. Okay, which diagram represents a parallel circuit with an equivalent resistance of 4 ohms. So we can eliminate 1 and 2 because these are in a series. So parallel. So the resistivity in a parallel circuit, we have 1 over Req is equal to 1 over R1 plus 1 over R2. Right? So we kind of just have to test it out, and you'll see that if we put like 1/2 plus 1/2, that's equal to 1. So Req is going to equal to 1, whereas 1/8 plus 1/8 is equal to 1/4. So the Req would be equal to 4. So for this one, the answer would be choice 4. Okay, all right. Diagram below shows 4 waves. Which 2 waves, when superimposed, would produce complete destructive interference at every point along the waves? So when you have like this interference, just think of them like you're combining 2 waves together. If we have a complete destructive interference, that means the 2 waves are kind of like mirror images of each other with respect to like the kind of like the axis. So if we look at B, that was a bad trace. B. And if we look at D, you kind of see how they're mirror images of each other. And when you superimpose them together, they would cancel each other out. So the answer is B and D. Okay. A musician plays a flute by blowing across the opening in the mouthpiece of the flute. This causes the air inside the flute to vibrate and produce sound waves. This phenomenon that creates these sound waves in a flute is called... So this appears a lot as resonance. And when you have like something that's like vibrating... it's resonant, so it might also be like when you're like hit like a fork and then like something else starts to vibrate. When you have these vibrations, it's probably resonant. diffraction, refraction, think about it, that's more about like the light, and the Doppler effect is more like when you have like sound that's like moving, like think of like an ambulance truck, or like a police car. Okay, compared to FM radio waves, AM radio waves. So let's look at the here. So AM has higher wavelength. Okay, well, actually AM have higher wavelength but lower frequency. So AM waves has, yeah, they have a longer wavelength. So 33 is choice 4. You just have to look here. Let me move this over a little bit, and you can see that the wavelength is on the top. The wavelength, like the scale's up there, and then the frequency is down there. Okay, all right. A star approaches Earth. Compared to the frequency and wavelength of the light emitted by the star, the light detected by an observer on Earth would have a. So it travels through So the light, it would enter the compared to. So therefore the answer is choice 3, yeah. Higher frequency. The frequency would increase. Oh, this is the Doppler's effect. Yeah, this would be the Doppler's effect because the star is approaching. So then you can kind of have to just remember a higher frequency and a shorter wavelength. Like think of it like I would say maybe think of it as the example of like a car when it's approaching towards you, right? Like the sirens will have a higher frequency, and when you have like a moving object that's like emitting like a wave, think of the Doppler effect. The wavelength will increase, and then if the wavelength increases, then the wavelength will have to if the frequency increases, then the wavelength will have to decrease. Okay. A beam of electron directed at a polycrystalline nickel target scatters to form a diffraction of patterns on a detecting screen. The diffraction of electron is an example of. So here, this is a definition question basically. It's wave nature of matter. So when we have this like diffraction of you kind of just have to remember, because matter, we kind of like talked about how like matter, like electron, they have both like particle properties, and so electrons have both particle properties and wave properties, and it's kind of like how matter can also have wave properties. Okay, all right. B1, it's gonna be not that long. Okay, what's the approximate width of 5 passengers in an automobile, of a 5-passenger automobile? So this tests you like a little bit of your senses. So it's gonna be like more than 2 meters, right? So it can be 1 or 2. So wait, hold on. Sorry. 5. Hold up. Okay, wait. It can't be less than 2 meters. So that's not. I think 2 meter is the approximation. I don't think it can be 20 meters. That's too long. So no, it can't be any higher than that. So it has to be 2. Okay. 2 identical metal spheres with a charge of positive 3 microcoulombs and negative 1 microcoulomb respectively are brought into contact and then separated, which statement describe the electrostatic force between the spheres. So the electrostatic force it's going to be attractive if they have opposite charges, and it's going to be repulsive if they have the same signs. Let me rephrase that. The electrostatic force is going to be attractive if they have opposite signs, and then it's going to be repulsive if they have the same sign. So at first, it's going to be attractive because they have negative, and then afterwards they're going to kind of like balance out, but actually, afterwards it's going to be okay. So at first it's going to be attractive, yes, so it can't be 3 or 4, but then afterwards you kind of have to look at like the movement of the electrons, and you kind of like it becomes like balanced out, and since before they're not in opposite, and when like the electrons move, both of them are going to be more positive, so they're going to be repulsive because they have like the same sign. Okay, which graph best represents the relationship between velocity and time for an object moving with a constant positive acceleration? So if it's constant positive acceleration, then the velocity would increase like linearly. So the answer to number 38 is choice 2. Okay, so Tiger ball kicked from PI at an angle above the horizontal field and lands on the field at point PF. Okay, as the ball travels from PI to PF in the air, the horizontal component of its velocity, we're neglecting friction here, so it's always going to remain the same. The answer is 4. Which graph best represents the relationship between the forces of kinetic friction and the normal force exerted on wooden boxes of various weight as they are moved at constant velocity across the wooden floor? So here we have constant velocity here. So that's like a keyword. Where's the between the kinetic and the normal force? Let me reread the question. Hold up. Which graph best represents the relationship between the forces of kinetic friction? Okay, kinetic friction is happening, and the normal force. Oh, as they are moved at a constant velocity. Okay. Here we're gonna look at the force of friction formula. So you should kind of like remember. Is it even on here? It is. So force of friction is equal to mu Fn. So there's a linear relationship between force of friction and Fn. I don't know why I read it as kinetic energy and that threw me off. So yeah, they have a constant velocity, so that means the net force is gonna be, well, don't worry about the constant velocity part is kind of irrelevant to this problem here. Okay, a 75-kilogram student runs up a stair, vertical distance of 13 meters in 25 seconds. The average power developed by the student is. So let's look at the power formula. Power formula is going to be, it's going to be work over time, and we find work by the force of the force times distance over time. So we're going to have P is equal to force times D over T. And what's the force here? The student has to run against gravity. So the force is his weight. It's going to be mg d divided by t. So m is 75. G, I'm going to use 9.81. And then times d, which is 13 divided by 25. So the answer is about 380. Answer choice 3. Okay. The diagram below represents an apparatus consisting of 2 conducting rails connected to resistor R and a copper wire of length D connected to each run, uniform magnetic field directed into the page. The electrons will flow through the resistor R if the copper wire is moving. So in order to produce a charge, the copper wire has to move perpendicular to the direction of the magnetic field. So it has to move left or right. So it would be choice 3. It has to move horizontally. Okay. The current through an incandescent lamp is 0.5 amps. So this is my current, the number of elementary charges. So we're looking for what's the elementary charges? Is it gonna be charge? So it's elementary charge, but it's gonna be well, Q that passes through the lamp in 5 seconds is gonna be T. Okay, so I is gonna be delta Q over T. So that means delta Q is going to be IT. And that's equal to 0.5 times 5, which is 2.5. But this is 2.5 coulombs. And now we got to convert it into elementary charges. So let's look at one of the constant here. 1 coulomb is equal to 6.25 times 10 to the 18 elementary charges. So I will multiply it by 6.25 times 10 to the 18 power to find the number of elementary charges. So that would give us 1.5625 E19. So this would be choice 43 will be choice 4. Okay. Base your answer, knowledge of physics. Okay, the equivalent resistance of the circuit is, okay, so we have a, here it's, so the resistors, they are, the resistors, they're in kind of like in series, so we just kind of add them up and it becomes 9. So 44, the answer is 4. Compared to the potential difference across the 6 ohm resistor, the potential difference across the 3 ohm resistor is, so for 45, it's going to be 1/2 as much, because of Ohm's law. Okay, which expression is a unit of work? So if we go to the work formula, this is what I like to do. I like to look at the work formula. Work is equal to force times distance. So work is equal to force times distance, and force is measured in newtons, distance is measured in meters. So is that any of the answer choices? No, not that. Okay. So Newton can be measured. So newtons of force. Force is so F is equal to MA. So that's equal to mass. So kg times meters per second squared times meter, which is kg times meter squared over second squared. And that's not one of the answer choices. So let's look at the other formula for work related to kind of like electricity. So I'm going to use W is equal to V squared T over R. And V is measured in volts, so that's V. Time is measured in seconds. And resistance is measured in ohms. So the answer for number 46 would be choice 1. Okay. The diagram represents a wave propagating to the right of the uniform medium. I represent. Okay. The particle is moving, so it's gonna move down. Because since it's going this way, right? Point A is gonna reach here and then reach here, and then just think about this, like the wave itself going like the wave itself is going this way, and then your A is gonna stay in the same axis. It's gonna move up and down. So since we have a transverse wave, it's not gonna be right. It's not gonna be left. Okay. A ray traveling through air-sprite's boundary with crown glass as shown. Which path would the reflected ray take? So would the incident ray, would it be reflected or would it be refracted? So 48, I think this one is pretty obvious. It would be B. It would kind of like go through, but the angle would bend a little bit, and that would be refraction. Okay. The diagram below shows wave fronts going through an opening and spreading into an area behind the barrier. This is what what sound is like. You kind of see this projection of sound, and this is called a diffraction. So the answer is choice 3. Resonance, we kind of explained earlier, is related to like when you have like something with like the same like natural frequency, and it will cause like other things vibrate. So that when you like hit a fork, it might cause like cups to vibrate. The Doppler effect, I like to think about it as like ambulances traveling towards you. You can hear like these sounds like at a higher frequency. And then reflection is something's being reflected. That one I think is pretty self-explanatory. All right. What occurs as an electron in a mercury atom moves from energy level B to energy level A? So we have mercury from B to A. Oh, it just so you see the energy difference. So if it jumps down, then a photon is gonna be emitted, and the energy is gonna be, so the energy that's emitted is it's gonna emit. I'm just gonna take the difference. So it's gonna emit 4.63 electron volts. So then now we gotta convert it into joules. So this is one of the things. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So I'm gonna multiply. I'm gonna multiply by 1.6 E negative 19, and that is choice 3. Okay. All right. That's it for the multiple choice. Hope this helps.